Hi everyone and welcome again. Let's begin by going to our hackdev folder, module 9, lab number 2. Okay, this time we have a binary program, POC-AES.exe, a ransom note encrypted, and a sample text file, which only contains a simple message. This is a sample text file. Okay, so let's open our terminal. Clicking this bar and typing cmd.exe. Okay, so now we can execute it. And well, we must provide a file path. Let's use sample.txt, and this generates another file with the same extension as the encrypted ransom note. We could try to view its content, and well, it doesn't make any sense. So let's begin analyzing the program. Let's open our tool Ghidra. Documents, Ghidra folder, and Ghidra run. We can close our file explorer. We close this tip window, and now we can import another file. We go one level up, lab number 2, and our POC. We click OK and wait for Ghidra to finish parsing the file. Here's the summary. OK again. And now we launch the tool. We click yes, leave the defaults and analyze. And now we wait for the analysis to finish. Great. Let's follow the same approach as the previous lab and inspect the imports. Okay, the interesting one is bcrypt. And now we see a different set of APIs. This time we have bcrypt encrypt. Bcrypt generate symmetric key. Bcrypt gen random. Bcrypt open algorithm provider, and so on. So let's begin analyzing the call to the open algorithm provider, because it can tell us what algorithm is using. Go to the references, and this looks like a wrapper, so we go to references again, and here it is. Here's the call to open algorithm provider. It's specifying AES, so now we know it's using AES encryption. The next thing we can notice is here it's specifying the mode. It's using CBC mode. Here is where it's creating its key. Well, actually it's importing the key, because this parameter specifies the bytes, the current bytes of the key, and the size as well, which is 32 bytes, which means it's using AES with 256 bits in mode CPC. Great. So now let's check what is actually encrypting. And here's the call: decrypt encrypt. We can start renaming some variables like this one. If we check the parameters needed, we can notice this is the size of the encrypted data. So let's rename it to encrypted length. Okay. And this is the initialization vector. So this is IV. It's specifying the size, 16 bytes, that's okay. And here, this should be a pointer to the buffer where the encrypted data is going to be stored. But this time it's a null pointer. This is because the program is trying to first get the size of the encrypted data. That's why we see two calls to decrypt encrypt. So now let's check where it's using this size. We can right click here and go to secondary highlight, set highlight, and well, we now can see where it's being used. Okay, so now it's used as the size of the output buffer. So this must be our out buffer. Okay, and that output buffer comes from this function and this another variable. Let's inspect. Okay, it calls another function to referencing the parameter, and this function simply returns whatever we pass as parameter. So we can rename this as red param. Okay, and this could be red pointer value. Okay, since it's referencing the parameter and returning that value. Okay, great. Then let's go check what is actually this variable. We can first remove all the other highlights and set the highlights for this variable. Okay, so this seems to be initialized with the encrypted length and nothing else before. It's simply defined as an array of 3 objects, 3 long integers, 8-byte integers. So this is most likely to be a vector because it fits with the structure. Simply three pointers. The first one to indicate the beginning of the data, the second the end of the data, and the third pointer is the end of the allocated space for data. So we can rename this variable to out vector, and this function should actually be std vector data. Great, which returns a pointer to the buffer of the data. Great. Let's move on. So now we know that the encrypted result is being stored in this vector. Now, if that function executed successfully, we now take some parameter and the extension enc we already saw executing the program. Then it's using the out vector, so this is the internal buffer, and it's calling a function over this object, that buffer, and this variable, which actually is being defined here, which comes from this another variable, local 340, which is the actual length of encrypted data. So this is using all the buffer of the encrypted data, and then it's destroying the key and closing the algorithm provider. So we may assume this could be the write to a file, because, well, this variable is being initialized with whatever this is, but here's involved the extension. So let's assume by now this is write to file. Okay, and well, as you may see, here's another write to file, which comes from this variable local 38. Let's go and check it. Remove highlights, set highlights, and let's go check where it's being defined. Oh, here it is. Great. Okay, so it's actually a copy of the IV, right? Because it's in a for loop over the 16 elements and simply making a copy. So let's rename it IV copy. Great. Let's go back, and now we can say the program is encrypting the content of the file and writing to the output file in the first 16 bytes the IP used, and then the encrypted data. Great. With that being said, seems like we are ready to decrypt our files. But first, we need to know the key used. If you remember, that key is being taken from this variable. Again, we could try to reverse engineer all the flow and get the value, or we can use the tool and intercept all the calls to decrypt generate symmetric key and simply dump the contents of this parameter. So let's do that. Let's open a terminal by typing cmd. We go to our folder, that is desktop, hackdev, and tools. Okay, if you remember, we need a clear text file. Let's write one, maybe clear text to cleartext.txt. Okay, so now we can execute NeZa. We provide a path to the program being analyzed. That is model 9, lab number 2, and this POC. Okay, that program itself requires another argument, which is our file clear text, and we specify API hooking b crypt generate symmetric key. Okay, we hit enter, and that's it. The hook was installed, and we intercept a call. Secret data length 32 bytes, and those bytes were written to this file. Let's try to dump it. Let's first clean our screen with CLS and use search util again. That is hooked, and there it is. We have our 32 bytes of the original key. Okay, so at this point we can simply write a program which reads the first 16 bytes of a file, extracts from that the IV, and then using this key decrypt the whole content. We already created that tool, so let's simply check it out so we can see in more detail what's going on. Let's open our text editor. That is Notepad++. And we open hackdev tools, and here it is, AES decrypt tool. Great. So for the usage, we must provide a path to the key file and a path to the encrypted file. Okay, so the first argument is key path, and the second the encrypted path. We use a helper function, load file, simply to load the content of the file in a vector. Okay, so we load the key. We have to make sure that the size is 32 bytes. We now load the encrypted file. Of course, the size cannot be less or equal to the block size, 16 bytes, because we already said that the first 16 bytes are the IV. So if the size is less or equal to that, then there is no data to decrypt. Now we separate the IV and the ciphertext. The IV is the encrypted data and the first 16 bytes, and the ciphertext is everything else. Great. Now we define a buffer for the decrypted output and start using the API. We again use open algorithm provider, specifying AES algorithm. We specify the chaining mode, CBC, just like the program, and now we generate a symmetric key or import the key. We specify key data, which comes from this vector, and the key size. Okay, and now we actually decrypt the data. We provide the IV and the output buffer. Okay, we simply resize to the actual size and print to the screen the amount of bytes of the decrypted data. Okay, and simply print the data, and that's it. Great. Now let's use it. Okay, then let's type the name of our tool, AES decrypt tool.exe, the path to the key, and the path to the encrypted file, which is cleartext.txt.enc. We hit enter, and there it is. Now we can see the recovered content. Great. So finally, let's try this with the encrypted ransom note. This time we'll provide the path to module 9, lab number 2, and ransomnote.txt.enc. We hit enter, and yep, we can now see the clear version of the ransom note. This is a test ransom note, all files encrypted. Note created January 1st, 2025 at 4 p.m. And great, I'll see you in the next lab. Bye.